In this video, we'll take a look at partial derivatives, and then if we get time, we'll take a look at the chain rule also. A lot of this is the stuff from Calc 1 now imported to Calc 3, so the stuff from 2 dimensions now adds that third dimension, and you're talking about derivatives, except you're talking about derivatives now in terms of f of xy instead of just f of x. Now, this guy who's hiking in the middle of this little valley over here, depending which way he goes, if he wants to find the slope at that point, like when you were trying to find the slope of a parabola at a certain point, and you picked that point over there, and you found the slope of the line, there wasn't any kind of question as to which way the parabola is going from there. It's only going in one direction. So there's your tangent line, there's the slope. But this guy going over here, he could leave in this direction, he could leave in that direction, he could leave in that direction. Depending which way he goes, he could end up with different slopes depending which way. I mean, obviously, if he goes forward, he's going to end up going down, and if he goes this way, he's going to end up going up. So those slopes are very different from each other. So that's why we have partial derivatives. What happens with partial derivatives is you take the derivative of a variable and then treat the other variables in the function as constants. So we do have some kind of funky notation. If you want the partial derivative of f with respect to x, those little d's in front tell me that I'm not taking df dx, I'm taking the partial derivative of f with respect to x. If you want sort of shorter notation, you can write it like that too, with the little subscript. So that says I'm taking the first partial derivative with respect to x. You can also take the first partial derivative with respect to y, and as it turns out, you can take second derivatives with partial derivatives also, but they get a little bit more complicated because now you've got more choices than just two. All right, in that case, you would treat the other variable or variables, depending how many there are, as constants. So if you want the partial derivative of f with respect to x, then you treat y as a constant and z and p and whatever else happens to be there. If you're taking the partial derivative of f with respect to y, then y is the only variable that you consider in the problem, and you treat everything else as a constant. Now, you can go through the pictures in the PowerPoint. It explains all about how you can use a limit definition to come up with a derivative. We will not do much with the limit definition of a derivative for these types of functions. We're going to focus more on the different rules for using them. So suppose I've got this function, f of xy equals x squared y, and I would like the first partial derivative of f with respect to x. So if I do that, I leave y as a constant, and I just worry about the x squared. So if I derive the x squared, I get 2x, and then the y just comes along, right, as a constant. If I were deriving 4x squared, I would multiply the 2 times 4. So here I'm deriving x squared y, so I multiply the 2x by y. Right, if I want the first partial derivative with respect to y, then the x squared gets treated as a constant, and you realize that when you derive y with respect to itself, you just get 1, so I'm just left with the constant. If you were deriving 7y, your answer would be 7, so if I'm deriving x squared y, my answer is just x squared. All right, the natural log of x divided by y. This one's going to involve a chain rule. So the first partial derivative with respect to x, how do I derive the natural log? I do 1 over the inside, so 1 over x over y, times the derivative of the inside. But this time I need the derivative of x over y with respect to x. So how do I do that? Well, isn't x over y the same thing as 1 over y times x? Well, if you tell me to take the derivative of 1 over y times x, it's just the coefficient, right? It's just that number in front. Let's simplify this. The 1 over x minus y, 1 over x over y is really y over x. Now multiply that by 1 over y. The y's go away. And the first partial derivative of f with respect to x is 1 over x. All right, what if I want the partial with respect to y? I'll rewrite these problems later. The first partial derivative with respect to y is going to start out exactly the same way. 1 over x over y. Now, times the derivative of the inside. Well, the inside is x over y, but if I want that derived with respect to y, why don't I call that, again, 1 over y times x? Now, if I take the derivative with respect to y, I end up with what? Well, actually, here, let's write it like this. xy to the negative first. use the power rule to derive that, and I get negative xy to the negative second, which is what? Y to the negative second means a y squared in the bottom, and I'll put my negative x up on top. All right, let's simplify this. The 1 over x over y becomes y over x times negative x over y squared. So there's a little canceling going on here, and I end up with a negative 1 over y as the partial derivative of f with respect to y. All right, let me throw on one that's not on the PowerPoint. Suppose I've got this problem. I've got f of xy equals x minus y over x plus y. And I would like to find the first partial derivative with respect to x of xy. So this time I'm treating y as a constant and x as the variable. This also involves the quotient rule. So now you got to go back to some of those rules from Calc 1 and carry them over. So it's going to be bottom derive the top, right? Low d high less high d low, draw the line, and down below, the denominator squared will go. It's beautiful poetry. So the bottom, there's your low. Now, derive the top. Derive x minus y with respect to x, and you'll get 1 minus 0, essentially, because the derivative of a constant is just 0. So there is your low d high, less high d low, so x minus y. The derivative on the bottom, derive x plus y with respect to x, and you'll get 1 plus 0 over the bottom squared. All right, simplify the top. Sometimes I will, sometimes I won't. In this case, it looks promising, so I've got an x plus y minus x plus y, right? Two negatives make a positive. So I end up with a 2y on the top and an x plus y squared on the bottom. All right, we could do that again for the partial of y with respect to xy, and we'll actually not get a very different answer. Bottom derive the top will be x plus y times. Now derive the x minus y up here with respect to y, and that becomes 0 minus 1. So now we get a negative 1. Minus high d low, so x minus y. The derivative of the bottom with respect to y is still 1 over the bottom squared. All right, when we expand and simplify the top, we get negative x minus y minus x plus y. So this time the y's go away, but the x's stay. So we got a negative 2x on the top, and we still have an x plus y squared on the bottom. So this is the partial derivative of y, the partial derivative of f with respect to y. All right, there was one down the bottom that I skipped, so let's slide this over, and we can take a look at that one. I figure let's do one with different variables besides x's and y's. Oftentimes our examples have only x's and y's in them, then we see a different variable and go, uh-oh, well now what? So f of pq equals the square root of p squared q to the third. What if I'd like the two possible partial derivatives here? Well, first of all, you realize that this is the same thing as p squared q cubed to the 1/2 power. So the partial derivative with respect to p of pq, the first part is going to be a plain old chain rule. So 1/2 p squared q cubed to the negative 1/2, right? Drop the power by 1. But now you're going to multiply by the derivative of the inside. So what's the derivative of the inside if you derive p squared q to the third with respect to p? The q to the third just stays, and you end up with a 2p q to the third. All right, and then you could simplify it from there, right? You could turn it back into a fraction. The 2 and the 1/2 will go away. You'll end up with a p times q cubed on the top and a p squared q to the third on the bottom. And actually a p knocks out top and bottom because the square root of p squared is just p. So you can end up with no p's. How about the q's? Well, all right. You'll end up with a q squared over the square root of q, And you can keep simplifying it from there if you want. If I want the partial derivative of f with respect to q, then what does this look like? It all starts out the same, right? The 1/2 p squared q to the third to the negative 1/2. But now when I multiply by the derivative of the inside, I'm holding that p squared constant, and I'm deriving the q to the third. So I end up with a 3q squared times the p squared that was already there, and then I can clean things up from there. So that's how you derive those functions as partial derivatives. Whatever you're deriving with respect to stays a variable, and then everything else is treated as a constant. So let's slide this over and take a look at the next step, which is what happens if I have second partial derivatives. And again, I got a couple of PowerPoint slides in the presentation. You can read through each of the details. Bottom line is you're going to have 4 different possibilities, right? You can take the partial derivative with respect to x and then derive it again with respect to x. You could take the partial derivative with respect to x the first time and then y the second time. You could take the partial with respect to y and then respect to x. You could take the partial with respect to y and then derive it again with respect to y. So you notice that the notation is you derive with respect to y, then respect to x. So the first one goes on the inside, the second one goes on the outside. This is the other notation for taking second partial derivatives. You're going to take the partial derivative of f with respect to x, then you're going to derive it again with respect to x. So inside, outside. Notice the way this one's written. The partial derivative with respect to y is done first, right? Order of operations, you do the stuff inside the parentheses first, then you take the partial with respect to x. So notice the y here and the x here. You could combine them in this second method over here, which is to say the second partial derivative of f with respect to y and then respect to x. With the shortened notation with the subscripts, you do it with respect to y, then respect to x. So it goes inside and then outside. And so there's 4 different partials. You can read through them all. Let's take a look at a couple of examples. All right, so here's a nice little polynomial. Relatively innocent looking polynomial. First of all, there's no product rule involved in here because the variables are only one. So I'm only deriving with respect to x or respect to y each time. So maybe the first thing is I should derive with respect to x and respect to y and then do my second step from there. Okay, so the partial derivative with respect to x is going to be what? Take that 5 and drop it in front. I'll get 10x to the 4th y squared. And then the second one, I'm going to treat that x again as the variable that I'm deriving. So I'll get a 2x times y. All right, what is the first partial derivative with respect to y? First partial with respect to y, now the 2x to the 5th is your constant. Drop the 2 from here in front, and I end up with a 4x to the 5th y. And then again, the x squared is your constant, so x squared, right? Derive something y to the first, becomes just that coefficient. So now, let's use that as our starting point, and now we're going to derive each of those with respect to another variable. So this first one over here says I've derived with respect to x, now derive with respect to x again. So let's take this first line, deriving with respect to x, and derive that with respect to x again. So that 4 that's in the top comes down, and I get 40x to the 3rd y squared, plus, now if I derive the second piece with respect to x, then I end up with what? Just the quote-unquote constants, which are both the 2 and the y. Okay, so that's the second partial with respect to x. All right, this one says first derive with respect to x, because that's the inside, then respect to y. So I've already taken the derivative with respect to x. Let's derive that same line now with respect to y. So the 10x to the 4th is our constant. Y squared is what we're going to derive, so the 2 comes out in front. 2 times 10 is 20. X to the 4th y. Right, if I derive this second expression over here, the 2xy, with respect to y, I just get 2x. Done. All right, now let's take the partial with respect to y and derive it with respect to x. So now we're done with that first line. Now we're going to come down to that second line. So let's take this partial over here with respect to y and derive it with respect to x. So over here, that 5 pops down in front. 5 times 4 is 20. Drop the power by 1. The y comes along. Derive x squared with respect to x, and you just get 2x. Now take this and derive it with respect to y. Well, the 4x to the fifth is your coefficient of y, so if you derive it with respect to y, the 4x to the fifth stays. Now derive x squared with respect to y, and something funny happens. There's just no second piece. Because if x squared is a constant and you derive it with respect to y, then that it's just done. Right? It's a constant, derive a constant, you get 0. All right, look at the two terms in the middle. Right? These two pieces in the middle here. Notice that they're the same thing. It turns out that in most cases that you're going to study in this book anyway, it doesn't matter which way you do those two derivatives. It doesn't matter if you derive with respect to x and then y, or y and then x, you're going to get the same thing. So sometimes it makes sense to derive one before the other, depending on what type of functions you have and what makes life a little bit easier, and sometimes what makes life possible. Again, let's take a look at an example that doesn't have x's and y's in it. Let's look at r's and s's. All right, if I want to find the 4 partial derivatives here, second partial derivatives, I might want to start by deriving this with respect to each of those variables first. So if I want the first partial derivative of q with respect to r, then I can think of this as r times 1 over s. Well, if I want the partial derivative with respect to r, then it's just the 1 over s. And if I want the first partial derivative with respect to s, then I can treat this as r times s to the negative first, derive it, and I get negative rs to the negative second. So negative 1, or I should say negative r, over s squared. Right, this first one, QRR, says derive the first expression that we have, Q with respect to R, again. Well, now if I derive this with respect to R, I just get 0. Because if I'm treating S as a constant, if I derive a constant, I get 0. That problem's done. All right, take that same expression and derive it with respect to S. Well, if this is the same thing as S to the negative first, and I derive it, I'll get negative s to the negative second. So this second derivative is negative 1 over s squared. All right, take the second expression, the negative r over s squared, and derive that with respect to r. Well, isn't negative r over s squared the same thing as 1 over s squared times negative r? What's the derivative of this thing with respect to r? It's just the coefficient. So actually I should tack the negative sign over here instead of over there. And now the coefficient is just negative 1 over s squared, which is not surprising because we were told that the two terms in the middle are going to be the same. Now take this thing and derive it with respect to s. So if my expression was negative rs to the negative second, and I derive that with respect to s, I'm going to get negative 2 times negative r s to the negative third. Right, you want to clean that up a little bit. The two negatives become a positive. The 2 and the r go up on the top. The s cubed goes down the bottom. All right, so that's how we take those second partial derivatives. What do we do if we've got 3 variables or more variables? Then you just keep deriving. So I've got a little problem here, the tangent of x, y, z. How can I find the partial with respect to x, the partial with respect to y, the partial with respect to z? These are all going to start the same way. The derivative of tangent is secant squared. So I'm going to end up with a secant squared xyz times the derivative of the inside. Well, the derivative of the inside with respect to x is just the yz. The derivative of the inside with respect to y is just xz. And then the derivative of the inside with respect to z is just xy. All right, so we can do it with 3 or more variables also. All right, this is the last one, I guess, from section 15.3, and then I'll start a new video for 15.4. This question asked about continuity, and I thought I did this in one of the other sections, but hey, it's never a bad idea to try it again. So I want to find out whether this is continuous at 0, 0. So I want to try different paths on the way towards 0, 0, because remember, you're approaching on more than one side on this surface, and you want to find out whether approaching on all the paths gives the same z value. So let's take x equals my squared, only because it's easier algebraically. If we can approach along lines, why not approach along parabolas? So replace these x's up here and down here with my squares. So I'll get 2 my squared times y squared over my squared plus y to the 4th, which gives me 2 m squared. Y squared times y squared is y to the 4th. On the bottom, I'll get an m squared y to the 4th plus y to the 4th. So on the top, I get a 2m squared y to the 4th. On the bottom, I got an m squared plus 1 times y to the 4th, right? My goal is to factor out a y to the 4th, so that becomes an m squared, but don't forget dividing y to the 4th by y to the 4th gives you 1. All right, so that gives me 2m squared over m squared plus 1. What if m is 1? Right, because that's a possibility. So what if m is equal to 1? If m is equal to 1, I get 2 times 1 over 1 squared plus 1. 2 over 2 is 1. 1 is not 0. That's your fact of the day. 1 is not 0. So I tried to fill that in with a 0 for my z value, but look at that, it didn't work. Next question is find the partial derivative of x with partial derivative with respect to x, partial derivative with respect to y. So let's take the original function, and I'll slide over here and look at it. I got a 2xy squared over x squared plus y to the 4th. And I want to take the partial derivative of f with respect to x. So I'll do one, and then you can fill in the blank from there. And the quotient rule pops up again here. So we're going to do bottom derive the top. So x squared plus y to the 4th times the derivative of 2xy squared with respect to x. So with respect to x, you just get what? A 2y squared. So low d high, less high, so 2xy squared, times the derivative of the bottom with respect to x. So deriving the x squared gives you 2x. Deriving a y to the 4th with respect to x just gives you 0, because y to the 4th is treated as a constant, all over the bottom squared. So the bottom squared is x squared plus y to the 4th squared. All right, let's do a little scratch work up on the top here, see if anything factors out. I'll end up with a 2x squared y squared plus 2y to the 6th minus 4x squared y squared. Okay, so it looks like the x squared y squared is combined. That gives me a negative 2x squared y squared plus a 2y to the 6th. So let's see, if I factor out a 2 and a y squared, then what's left? In this first term is just a negative x squared. And then in the second term, I drop this down by 2, and so I get a plus y to the 4th. And then down the bottom, x squared plus y to the 4th squared. So that's the first partial derivative with respect to x. I'll bet you the first partial derivative with respect to y also goes very similarly. All right, and that's the end of this section. We'll do the chain rule in the next video.